morning. Welcome to the third day of the Gyan course. So, what I intend to cover today is mostly flow boiling and condensation, and but there are a few topics from pool boiling I would like to still address in the afternoon, okay, because it has bearing to condensation heat transfer as well. So, today the plan is to first start with flow boiling. I intend to discuss a homogeneous model and then talk about separated flow model, okay. And then I will show you some results that we have in our research group, where we did flow boiling on carbon nanotube coated heaters, and we found there was a enhancement, but the level of enhancement we got was very counterintuitive, okay. And to explain that result, we have to resort to this particular correlation called Chen's correlation. So, there are multiple correlations on flow boiling and condensation, because this is a very short and condensed course, I won't have time to do an exhaustive review of all the flow boiling correlations that are out there. I am going to cherry pick a few correlations that we found were very consistent with our experimental data as far as nano coatings are concerned, okay. So, I am going to focus on those, and similarly we did some work in compact condensers, microchannel condensers, where we did coating of carbon nanotubes, and the condensation heat transfer improved as well. And so that also was a very counterintuitive data. So, I am going to discuss that as well, and probably that is going to be in the afternoon, okay. And in terms of the coursework today, I am going to start off by showing you a few videos about multi-phase flows. Unlike single phase flows in a pipe, where you can sort of estimate the friction factor as a function of Reynolds number, or you can estimate the Nusselt number or heat transfer coefficient as a function of Reynolds number, and all you need to care about is whether the flow is laminar or turbulent, okay. Typically, the orientation of the pipe is not that much of an issue, okay. But in two phase flow, you get different flow configurations, and the interesting thing is how the pipe is oriented can change your pressure drop or your heat transfer by a factor of 10, okay. When we have a straight pipe or a horizontal pipe or a vertical pipe or an inclined pipe, and we are doing a single phase flow calculation, all we need to do is just account for the hydrostatic head, right, and that seems to do the job. And we do not expect a factor of 10 difference in heat transfer or pressure drop, just because the orientation of the pipe has changed. But in two phase flow, the orientation makes a big difference, okay. And there are some studies that are suggesting also that in certain flow regimes, your surface properties also make a big difference, okay. So, so let us look at a few videos, and then we will have a philosophical discussion before we dive into the math. That sounds like a good deal, okay. So, let us look at a few videos first, and I wish I had time to show you some more, but I'll restrict myself. Oh my goodness, now my internet connection is not working. Let us hope it works. Okay, this one works. So, let us okay. Let me pause this for a second, okay. So, what you see over here, okay, I do not know what happened. Cable গন্ডগোল কি? Finally, okay, thank you. So, what you see over here is a flow coming in at the bottom. You can see the pipe is horizontal, right, and this is a classic example of a stratified flow, where you have air flowing on the top, and this one does not involve any heat transfer. So, this is a adiabatic flow is what you are looking at, okay. So, and so you have a classic example of a stratified flow. You have liquid in the bottom, gas on the top, air on the top, But then the interesting thing is the moment it goes vertical, it goes around a bend and goes vertical, you will see this stratified flow will turn into sort of like a bubbly flow and a churn flow. And what do I mean by those? I will come to that in a minute. And then it goes through a bend, and when it is a downward facing flow, you can see again it has taken a sort of a mixture. One part of the pipe is in stratified flow, the other part of the pipe is in bubbly flow. And then it goes, that same flow goes through at an angle, and the whole flow configuration changes. Okay. So, orientation and gravity make a big difference when it comes to two-phase flow, okay, in addition to surface characteristics, and this is the most simplified situation you can think of where you do not have any heat transfer, is not it. Okay. So, let us look at the video. Okay, so let us pause for a second. Okay. You can see very nicely, you can see the bubbly flow regime, and it is almost homogeneous. The bubbles are almost homogeneously distributed in the whole cross section of the pipe, whereas in the bottom you can see it is sort of a separated flow, right. And then here it is a mix of, one part is bubbly flow and the other part is stratified. I mean, you have a mixture of bubbly flow and stratified flow when it is going down essentially. Okay. And then you see also a classic example of churn flow. Time to time, there is the void fraction, the amount of gas in the cross section increases and then decreases, then increases, then decreases, and this causes flow reversal. A part of the flow actually is turning back on itself. Okay. I am going to show you a high speed video in a very slow motion, and you can see this classic example of the flow turning on itself. Okay. Now, here is another interesting example. Let us say I want to measure this flow rate. Okay. What kind of flow meter should I use? What do you think? Come again? Orifice flow meter? So, how would the orifice flow meter work? Go ahead. Come again? A what? Wire and notch flow meter. How would that work? Mm-hmm. No, but when you are going through the upward moving thing, is this a sound? Okay, great, thank you. So the upward, when it is moving upward, you have a homogeneous distribution. You don't have a free surface. But I want a flow meter that will work for all the flow regimes, right? Okay. So what other options do I have? I mean, you are all engineers over here. You start your job on day one. Your boss comes to you and says, "We have this project. We got to measure the flow rate in two-phase flow. What flow meter do you want to use? What will you tell your boss?" Come again? Can we just? PIV. Well, for PIV to work, you need access to the complete flow cross section, right? But you have lots of bubbles in between. So the bubbles will mess up your PIV autocorrelation function. Okay, so here they show that the conventional way that people use is they use a turbine flow meter. But the problem is, if you use a turbine, I mean that's a common standard. okay, but even that creates complication, because the moment you put a turbine flow meter, it messes up the whole flow regime. So, the act of measurement starts affecting your system. Okay. So, just look at it. Oops. What you can see is, because of that turbine flow meter, the flow goes up and down. The vorticity induced by the turbine flow meter, and so therefore the measurements you are going to make with your turbine flow meter are going to be wrong, because turbine flow meter relies on uniform rotation at a steady state. Okay. Okay, so pay close attention. On the topward portion, it's one type, it's decelerating. On the downward portion, it's accelerating, and so on. Okay, so now let's look at a slow motion. Okay. Here's something. Oops. The internet is getting flaky on me. Any of the Kharagpur students, can you help me with logging into the campus, I guess? Because this one, okay, now it looks like it's working. Okay, so this one is a video that shows in slow motion a bubbly flow. Oh, no, this one is the wrong video. No, this is not the video I wanted to show you. You know what, let me fix this during the time of the break. Looks like the internet is very flaky. I'll come back to the slow motion for the video, okay, after the break. So now let's do a philosophical discussion. Okay. So the philosophical discussion is, when it comes to critical heat flux, what determines your critical heat flux? What determines, so for example, what is the bottleneck here, right? They say the weakest link in a chain is the strength of your chain link, right? Or in other words, the slowest parameter is your limiting parameter, right? So when it comes to critical heat flux, what is that limit that determines your critical heat flux? Is it the maximum rate at which you can pump heat into the liquid, or is it something else? what did we say was the limiting factor? No, I am talking about CHF itself. What determines that CHF is reached? Is it the rate at which you produce vapor bubbles? Is that the limit? Or is it the rate at which you can take the vapor bubbles out of your system? What do you think is the limit? Which is the weaker link? Is the slower process the rate at which you can produce bubbles, or the rate at which you can get the bubbles out of your system? Which one is the slower process? It's kind of like a relay race, right? The slowest runner is what determines who gets the medal or not. It's not the fastest runner, isn't it, in a relay race? So here you have 2-person relay race. There is one part of your system that is producing vapor, and there is one part of the system that is taking the vapor out of your system. So which one is the slow guy? The rate at which you can, so in other words, the rate at which you can take vapor out of your system is the limiting factor here. Okay. So in other words, if as a function of delta t, if I plot q double prime, the rate at which you are producing vapor after about 4 degrees Celsius, your vapor production starts, right? So the rate at which you can produce vapor is given by this line, right? And the rate at which you can take vapor bubbles out of your system is where your critical heat flux comes in, because if you produce more vapor than your vapor removal limit, what happens? It starts forming the blanket, isn't it? So this is the limiting factor that determines your CHF. Yeah, agreed? But if I start having flow boiling, then this limit is gone, because the moment a vapor bubble is produced, I can pump at really high speed and take the vapor bubble out of my system, isn't it? So here the vapor removal limit is your terminal velocity of the bubble, right? But the moment I have a flow boiling happening where the bulk of the liquid flows, then I have done away with this limit, because now my flow rate determines how fast I can take the vapor bubble out of the system. Okay. Then the fundamental question is, what is the limit of producing vapor bubble? Okay. Then I need to figure out where the evaporation limit is. Does that make sense? Yeah. So how do I figure out what is the evaporation limit? And that's a fundamental thermodynamic question. Okay. So that means if I take a liquid molecule and take it to the vapor phase, it has to jump through that liquid vapor interface, isn't it? And that's the fundamental resistance that will always be there, whether you have flow boiling or pool boiling, right? And that limit is probably much higher than your vapor removal limit. Okay. So that fundamental thermodynamic limit is the vapor production limit. Isn't it? And I need to figure this one out. Oh, sorry. So I need to figure this vapor production limit in order for me to know what is the maximum possible heat transfer I can get in a boiling system, whether it's pool boiling or flow boiling. Make sense? Right. So the concept that is used to figure out this vapor production limit is what is known as evaporative resistance. Okay. So I can use the fundamental laws of thermodynamics to get an estimate for the evaporative resistance. So we will derive the equation now, and then I am hoping I will have enough time in the afternoon that we can do some calculations and see what that evaporation resistance value typically is for water, for example. Okay. So, in order for us to figure out the evaporative resistance, okay, so remember when we were deriving the Young Laplace equation, we said that you have a vapor layer, you have a liquid layer, and then you have a interface layer, right. And so this interface layer is sometimes known as the Knudsen layer. Okay, so if I have a liquid molecule and it wants to go into the vapor phase, it has to cross through this barrier of the Knudsen layer. Okay, so we can use ideal gas laws. So if I want to figure out the number density of molecules in the liquid and the number density of molecules in the gas, so the number density of molecules in the liquid is P divided by R is your fundamental universal gas constant. So P by RT gives you what? Come again? Density, right? Okay. So if I divide it by the molecular weight, it gives me the moles, and then if I multiply it by Avogadro number, it gives me the number of molecules per unit volume, right. Similarly, I can write down my NL to be equal to, so this is Pg, similarly I have PL divided by RTL, right. And then I know from kinetic theory of gases, the average speed of the molecules is given by okay, so that's average speed in the gas layer, average speed in the liquid is okay, and so the mass flux is the number density of the liquid times the average speed of the liquid divided by 4 minus number density of the gas, average speed of the gas by 4. So in other words, liquid molecules are moving into the vapor with a speed of CL, isn't it, and gas molecules correspondingly are coming in, or the vapor molecules are correspondingly coming in into the liquid with a value of Cg. And so the difference of these two fluxes is the net rate at which I have evaporation happening from the liquid to the vapor. Does that make sense? Yeah. So if I substitute the numbers and I make the assumption that the temperature is the same in the liquid in the gas, so TL is equal to Tg is equal to Tsat. Okay, if I make that assumption, okay, Jm, the net mass flux from liquid to vapor, comes out as PL minus Pg divided by M times Na, and then I get 1 by RT sat to the power of half. Okay, and then my heat flux then is nothing but Jm times HFG. Okay, and then I am going to make another assumption. I am going to use Clausius-Clapeyron equation, which tells you that PL minus Pg. What did we say was the Clausius-Clapeyron equation? Can somebody remind me? You have it in your notes from yesterday. You can look it up. Come again? Okay. Mm-hmm. Is that what it is? Okay. Rho g. So, rho g HFG by T sat, nothing else. There should be a, okay, so that should be a delta T, right. Okay, so if I substitute it, I will get my Q double prime to be equal to delta T times Na by M times rho g times HFG square divided by T sat, or the instead of rho g we can write it as VFG in the denominator, right. And what else? And then I have a root of 2 pi r times T sat, isn't it? And so my evaporative resistance R evaporation is nothing but voltage divided by current, right, that is my resistance. And so that comes out to T sat times VFG times 2 pi r, the gas constant, times T sat divided by HFG square. And if I assume that VFG is nothing but 1 by rho g, I can simplify this further and write it as T sat times root of 2 pi r T sat divided by rho g times So, remember this equation, because when we deal with two phase flow, particularly when you have evaporation happening, you might end up with a situation where you have a thin film of liquid that is thinner than the size of your bubbles, which means bubbles cannot nucleate anymore. So, you are going to rely on thin film evaporation for heat transfer, okay. And in thin film evaporation, this is the rate of heat transfer that you are going to get. This R evaporation can help you estimate the amount of heat transfer you will get in thin film evaporation. Does that make sense? Okay. Now, there is one more fundamental philosophical discussion I wanted to have with you before we dive into the actual guts of the two phase flow and the different flow regimes. And so, that is basically going back to Helmholtz instability. Okay, so what did we say was Helmholtz instability, the UG minus UL critical, what was that equal to? Can somebody help me out? Okay. Well, I wanted the more general one. So, the more general one was 1 by rho L plus 1 by rho G, right. Yeah. And then I can make the substitution that my K is 2 pi L naught, okay, or some multiple of 2 pi L naught, and then this 1 by rho L plus 1 by rho G, I can approximate it as 1 by rho G, right. So, then and then the square root of this whole thing. So, then it becomes 2 pi sigma L naught. I am sorry. Yeah, it should be divided by L naught. You are right. It does not matter. It is the magnitude. because it is a square. We are writing UL minus UG square essentially. So, it can be either one of them can be bigger one, and so all I care about is the magnitude of this one. Okay. So, so that is a simplified equation, is not it? So, consider a situation, and this is particularly true when you are dealing with flow in gas pipelines. Okay, and you saw in the video that I just showed, you can have a situation where you have stratified flow. Okay, you can have a part of the fluid being liquid in the pipeline, and the other part of the pipeline can be a gas, the vapor. And these are not pure, these are probably mixture of different hydrocarbons. So, depending on the pressure, your concentration of the different components in the liquid and the gas will change, because the lower volatile materials might be more in the gas phase and less in the liquid phase, depending on the pressure and temperature condition as the pressure drops along the pipeline. So, it is a very complicated problem, right. But what Helmholtz instability is telling you is there is a maximum limit to which you can do pumping. Okay. Does that, do you understand that? Because what happens is, if your pumping rate exceeds a certain value such that the difference in velocity. So, if I look at it in the side view, okay, my liquid vapor interface, my gas is flowing with a certain velocity, my liquid is flowing with a certain velocity, or let us call it UG and UL. And if the difference in the velocity of the two phases exceeds this critical value, what will happen? What do you think is going to happen from an instability point of view? So, what do you mean by unstable? So, these oscillations that are there on the surface, the waves that you are going to form, these waves are going to grow in amplitude. So, you are going to get a lot of sloshing motion, and eventually a part of the waves might go and hit the top surface of the pipe. Okay, or in other words, the flow will start breaking up the liquid phase and start generating droplets and mist. And pretty soon you will end up with a situation where the gas phase has a lot of mist in it. Okay, so, the average density of the gas phase will go up. Okay, and that will lead to its own problems with respect to pumping and the pressure drops and the flow rates. Okay. So, when it comes to two phase flow, this Helmholtz instability that we looked at, it is not only valid for pool boiling, it is also valid for flow boiling, particularly when you are dealing with stratified flow. Okay. And so, this Helmholtz instability can theoretically predict the maximum flow rate or pumping rates that you can use in your pipeline. Okay. So, that is the beauty of instability theory. We have not even looked at the different flow regimes, and we are already making predictions, right. So, now let us dive into the two phase flow, all right. So, as I mentioned, depending on your configuration, you can get different types of flow regimes. The same mass flow rate and everything else, if I convert the horizontal pipe to a vertical pipe, whether you have an upward flow or a downward flow, things will start changing. Okay. So, now let us look at the most simple configuration, that is of a pipe, vertical pipe with a upward flow, okay, because you do not have the asymmetry. When you have a horizontal pipe, then you have asymmetry, because of gravity the higher density phase will tend to stick towards the bottom portion, the lower density phase will tend to stick to the upper portion. So, you will end up with complications when you have a horizontal flow. When you have a vertical flow, things tend to be more axisymmetric and less chances of asymmetry in your flow, and therefore, it is easier to do the predictions. Okay. Now, the other fundamental problem with two phase flow is there is a lot of oscillations that go on. Unfortunately, I could not show you the video now. When I show you the video after the break, you will see that on a local basis there are a lot of flow reversals that happen, and what that causes is a part of the flow to move back and forth. Even though the bulk flow is in one direction, the local flow can get in the opposite direction. Okay? And because of that, you have oscillations and instability in the flow as well, and therefore, even if your pump is pumping at a constant flow rate or at a constant pressure, on the output side, the rate at which the flow comes out can oscillate or sputter with time, and so therefore, making those predictions become even more hard, and you sort of give an average prediction. You cannot really do a local prediction or a transient prediction. It becomes very difficult to do a transient prediction, and as a result, the same experiment, you repeat it the next day, you can be off by a factor of 20 to 50%. Okay, in two-phase flow, if your answer is within 20 to 30%, you are happy. You consider it to be a repeatable experiment. Okay, just because of these issues. All right, so your precision of prediction and the precision of repeatability in your experiments actually varies quite a bit. All right, so let's therefore go into a vertical flow configuration, and so the simplest way to do it is what is known as adiabatic two-phase flow, which is if you don't have any heat transfer. Okay, so let's look at the adiabatic two-phase flow first. So in adiabatic two-phase flow, typically, and there was another video also I wanted to show you, that how you introduce the gas phase into the liquid pool also makes a big difference. So let's say I have a pipe that's going in the vertical direction, and I have a uniform flow of liquid UL in the pipe, fully developed flow. Okay. Now I can introduce a small nozzle, and the shape of the nozzle, the size, whether it's porous or non-porous, all these things will affect your answers. Okay. But let's just forget about those complications. Let's assume how you introduce the gas phase doesn't matter at this point, and let's say you introduce a air at a very small flow rate. Okay. So you are going to end up with small bubbles that form in the flow, and they will sort of orient themselves homogeneously around the cross section of the pipe. Okay. So you end up with what is known as bubbly flow. Okay. And then if I keep increasing the rate of my so you have mass flow rate of your gas and you have mass flow rate of your liquid. Okay. So in order for me to characterize how this flow happens, I need to come up with some standard terminologies for two-phase flow. Okay. By the way, how are we doing on time? Do you all want to take a break, have some tea, and then come back? It's been almost 1 hour now, right? Yeah, we started at no. Well, it's only 40 minutes. Well, let's do another 20 minutes and then we will take the break. Sorry. So one of the fundamental parameters that we are interested in is known as the quality. Okay, and so the quality is how much of my total mass flow rate is the gas phase or the vapor phase. Okay, and we know this from your undergraduate thermodynamics. So that's the definition of quality. Okay. Now we also use another parameter which is known as void fraction. Now unlike quality, which is a very standardized definition, the definition of void fraction actually varies quite a bit. Okay, and to a large extent it's because of the type of measurement technique you use to estimate this parameter called void fraction. Okay, the quality is very easy to determine. Okay, you have a two-phase flow in a pipe, you just bleed it into a container, measure the amount of liquid that you collected, the rest has escaped as vapor. So therefore you know what the quality is. You can measure, collect the liquid over a certain amount of time, and from that you can estimate, or you can condense the other one. Essentially, if it's pure vapor, you condense the vapor and you know how much was vapor, how much was liquid, and that's a fairly straightforward calculation to do. So therefore there is not much of a big variation in terms of how quality is measured or quality is defined. Okay. Now with respect to the metrology technique for the void fraction, your definition of void fraction changes. Okay. But the most fundamental definition of void fraction is if I take a pipe and let us say a part of the pipe, if I take a cross section at any location, and if I can measure the area occupied by the gas versus the area occupied by the liquid, the most fundamental definition of void fraction is Ag divided by Ag plus Al. Okay, and typically this measurement can be done by using things like X-ray tomography. Okay, so you illuminate it with X-ray and you can very clearly visualize how much is gas, how much is liquid. But X-ray tomography is a very specialized measurement technique and it is very expensive also. Okay, so not all commercial operations will have the luxury of doing a X-ray type of measurement. Okay, so in other measurements, what they do is they can use orifice meter, for example, okay, or there are other ways of doing it in terms of the volume or in terms of the flow rate. Okay, and so depending on the measurement technique that people are using, this definition can be based on the velocity, it can be based on the volume flow rate and so on. Okay, but the most fundamental definition of void fraction is what I have given you over here. Does that make sense? Okay. Now, there are a couple of other terminologies that one has to look at, and those are what are known as mass average velocities. Okay. Now, I won't spend too much time on the two-phase flow fundamentals, because one thing I realized while I was generating the notes for this class was there are some really good NPTEL courses on two-phase flow. Okay, and those courses have been recorded over like 7 or 8 week period instead of 1 week like we are doing here. And so therefore, the information that you get in those NPTEL courses is much deeper and stronger, and there is more time to discuss the nuances essentially. So let's see. Now, so just like you have a vapor void fraction, we can call it alpha f, alpha g or alpha l. No, sorry. You can also have something known as the liquid void fraction. I will come to the mass averaged velocities a little later. Okay. So you can have a liquid void fraction, and that is defined as the amount occupied by the liquid divided by the total area. Okay. Now, you also have what is known as mass superficial fluxes. So, the superficial flux for gas is defined as J sub g, and that is let us see. That is defined as the total mass flow rate divided by the gas flow rate of the gas divided by the area divided by the density of the gas. So, that kind of gives you a average sense of the average velocity of the vapor. So, if all of the vapor were to flow through the whole cross section of the pipe, this A is the total A. Okay, or in other words, we can also define what is known as a let us see, a mass velocity. Okay, so let us define the mass velocity first. Okay, so mass velocity is defined as the total mass flow rate divided by the total area. and so the mass velocity divided by the density. So, the superficial flux for gas, I call it as Jg, and that is equal to G times X is the mass flow rate of the gas divided by rho g. And similarly, I can define a superficial flux for liquid, and that is called GL, I mean JL or JF, and that is G times 1 minus X divided by rho L or rho F. Okay. So, J has units of velocity, and it is an indicator for volume flow rate. Okay. Now, so if I increase the void fraction in my flow, this bubbly flow will now end up with bigger bubbles. Okay. In bubbly flow, the size of the bubbles is very small compared to the total diameter of the tube. Okay. But if I increase the mass flux of the mass flow rate of the vapor bubbles or the gas bubbles in this flow, now I am going to end up with bigger bubbles. Or if I give this flow sufficient length to flow, eventually these bubbles will start coalescing and forming bigger bubbles. Okay. So, it could be either way. If you have a long enough pipe, or if you have a short pipe with a very high velocity of gases, or with a high mass fraction of the gases, or higher quality flow, you will tend to get bubbles that are bigger in size and almost the same dimension as your pipe. Okay. So, when you have a flow where the bubbles are of the same size as your pipe dimension, then I am ending up with this slug flow, okay, where the size of these gas bubbles are almost rather same order of magnitude as the diameter of the pipe. Okay. And eventually what you have is these slugs, they start joining up and they start forming longer columns. And the problem with having very long columns of vapor bubbles moving is, as they are moving up, they are displacing the liquid, and so the liquid tends to flow in the downward direction, while the vapor tries to, or the gas tries to move in the upward direction, and then behind the gas bubble they start moving back once again. As the gas bubble is leaving, the liquid starts occupying that volume. So, all that flow comes in and then starts following the gas bubble. Okay. And so, then you have churn flow, and the problem with churn flow is you get localized areas of flow reversal. Okay. And then if these churns start joining up at really high vapor velocities or gas velocities, or at really high values of mass fraction, then you end up with what is known as annular flow, where the liquid is on the edge and the rest, the core of the flow is gas. Okay. And then if you do end up violating the Helmholtz instability criterion, okay, then a part of the liquid actually starts getting entrained in the vapor or the gas. Okay. And so, you can get what is known as wispy annular flow. So, this is annular flow, and then you get what is known as wispy annular flow, where you have the annular flow as usual, but now your gas has a lot of entrained mist in it, or small droplets in it. Okay. So, it is known as the wispy annular flow. Now, how do you know when you are going to get bubbly flow, how do you are going to get annular flow, when you are going to get churn flow. Okay. So, to answer that, there was one fundamental study that was done by that was originally so Hewitt was kind of pioneer in that direction in trying to make this thing more standardized, and so Hewitt came up with what is known as flow maps. Okay. And so and this is in your notes, so you do not have to copy it, you already have a PDF copy. Okay, you will probably have to rely on the projection system. Okay, let me draw it on a piece of paper. Is it the intensity is too high? Oh, much better. Okay. So what Hewitt, what they proposed was this is kind of like a momentum map. Okay. So what you see is rho g times jg has units of velocity, right? So this is kind of like rho v square. So this gives you an estimate for the momentum in the gas phase. This gives you an estimate for the momentum in the liquid phase, and depending on whichever one has a higher magnitude of momentum proportionately, that particular flow dominates. So if my vapor phase has a higher momentum, then it will occupy the bulk of the flow, and so therefore I am sorry, if the gas phase has a higher momentum, so therefore your annular flow is characterized by high gas momentum, low liquid momentum. On the other hand, if you have high liquid momentum and low gas momentum, then you are more likely to have bubbly flow. Okay. And so you could be starting here, then you could be going into slug flow, then churn flow, then wispy annular flow, and then annular flow. Or you could be starting in churn flow, going into annular flow, and then into wispy annular flow. Okay. So this is one example of the flow path. As the flow progresses through the pipe, this shows one path of your apparatus. So depending on the flow conditions and the history of the flow, you could be charting different types of flow paths. Okay. So basically this is one way of characterizing your different flow regimes. Okay. So this is known as a flow map. Now this one is based on adiabatic two-phase flow, where there is no heat transfer. Okay. When there is a heat transfer, then there is a different way of characterizing it. Okay. We will come to that in a minute. So anyway, so this is how you is one standardized way of estimating in which part of the pipe you have which type of flow. Okay. And then if you change the pipe diameter, you change the pipe orientation, for each of these different parameter or configuration, you have to generate a separate flow map. Okay. So this is not standardized, and it is very specific to the particular experimental apparatus you have. And so that is one of the enigmas of two-phase flow, is there is no standardized Moody diagram that you can use. Okay. So for whenever you are designing a new system, your only recourse is to go do experiments, because there is no standardized chart that you can use. So if you change the diameter of the pipe, the whole flow map changes. Okay. So you might have generated a flow map for 5 millimeter diameter pipes, but you cannot use it for 8 millimeter diameter pipes. You will actually have to go do an experiment and generate the flow maps for 8 millimeter pipes. Okay. That is the main problem, if you want sufficient accuracy. Okay. This could be a good starting point, but then again this one, the answers could be off by as much as 50 to 100%. You could be off by a factor of 2. Okay. So if you want more accuracy and precision in your experiments, you better go generate a flow loop for that particular diameter or for that particular orientation and generate your own flow map. Okay. Go ahead. You can do simulations, but simulations by themselves do not mean anything unless you can do experimental validation. Okay, and it is very difficult to do simulations for the all of the flow regimes. You can probably do it for churn flow, maybe slug flow. Doing a simulation for bubbly flow might be difficult. You use what is known as homogeneous model, which we are going to look at next, but your accuracy is only so much. Go ahead.
So can you do some sort of dimensional analysis to get a understanding of a different geometric form also?
Yes. The fluid mechanics book by Fox, Pritchard, McDonald, if you go and look into the chapter where they discuss the dimensional analysis, they show you that there are certain situations where dimensional analysis fails. Okay, so they have a very classic example of a ship moving in the ocean, which is an example of a two-phase flow, right? And there they show that dimensional analysis actually fails. So when it comes to two-phase flows, your dimensional analysis is applicable in only a very narrow window. Okay, and we can discuss this after the class also, but when it comes to two-phase flow, dimensional analysis only goes so far, and it is not universally applicable. There are situations where dimensional analysis actually fails. Okay. So in other words, you can never win with two-phase flow. You actually have to go and do the experiment if you want sufficient level of precision. Most of the analytical methods or computational methods are still inadequate because of the complexity and the transient nature of the whole process. Okay. All right. So now, all those individual lines that I showed you on the flow map, there are correlations. Different people have come up with different correlations to tell you what those lines are. Okay, but in the interest of time, I am skipping that part because this is more about recent advances rather than what was done in the 60s and 70s. I am just mentioning so that everybody is on the same level, so we can have a more nuanced discussion when it comes to the more recent topics. Okay, and then if you want to learn more about these, I think NPTEL has a bunch of multi-phase flows, lectures and more detailed. Essentially, I would recommend that you go and look into it. In particular, I can tell you over the break, which particular NPTEL courses I would recommend. Okay. So now one of the fundamental parameters that we use in discussing two-phase flow is known as what is known as Martinelli parameter. Okay, and it is denoted by capital X, just like small x denotes the quality. Capital X is known as the Martinelli parameter, and this is a very fundamental parameter that is universally used both in flow boiling and condensation. Okay. So the Martinelli parameter is defined as the pressure drop in the liquid phase divided by pressure drop in the gas phase. Okay, so if I have single phase flow, if the velocity is u, the length of the pipe is L, okay, what is my dP dz? Oh, it is not showing up, sorry. So how do I define my dP dz when it comes to single phase flow? Or let me ask you how much is the pressure drop? Let us say it is laminar flow. Yeah, so what is that equation? Come again? So I will have F L by D times is there a rho or there is no rho? half rho u square, right? Okay. What if I write it in terms of mass flow rate? So, instead of u, if I write it in terms of m dot, come again? Is that all? So, I can write down my u as m dot divided by rho a, and that is it. Or well, if it is a circular pipe, then I can write it in terms of d, right. So, how much will it become then? And instead of using this Darcy friction factor, what if I write it in terms of fanning friction factor? Okay. So, in the interest of time, I will write it down. So, that will be equal to F times m dot divided by A square divided by rho d. I am sorry, F yeah. Okay. So, if I apply that equation here for the Martinelli parameter, my dp dz. So, my dp dz in that case is f by I am sorry, delta p by L, right. Okay. So, my dp dz for the fluid side will be equal to, and there will be a factor of 2, I missed that. So, that will be 2 times the friction factor associated with the fluid times the m dot by A for the fluid square divided by rho f times d. And so, m dot by A we called it, what did we call the m dot by A? Mass velocity, right. So, I can represent it by g essentially. So, I can write this as 2 times, and so this would be m dot f, I am sorry. So, this would be 2 times the friction factor times g times 1 minus x whole square divided by rho f times d. And similarly, I can write down the dp dz for the gas side to be equal to 2 times the friction factor times g times x square divided by rho g d. Okay. And then if I take the ratio of these two pressure drops, that gives me the Martinelli parameter. Okay. Now, when you have boiling or evaporation happening or condensation, the value of x is going to change along the flow direction. Okay. So, you will have different values of Martinelli parameter in different parts of your pipe. So, the way to do it is you chop your pipe up into different computational volumes and you calculate the x at each location, and once you know the x at each location for that small chopped volume, you can calculate what the dp dz will be, and therefore, you can calculate what the Martinelli parameter will be for that portion of your computational volume. Does that make sense? So, you can do this on a Excel spreadsheet or in a code, right, and that is how it is implemented in practice. Okay. So, the value of Martinelli parameter is not constant all through the pipe, it is going to change at different locations, and so depending on how fine you make your computational mesh to be, the finer distribution you have of your quality and the Martinelli parameter. Okay. So, now this friction factor F will be different when you have laminar flow and when you have turbulent flow. Okay. So, so how do I define my friction factor F? My friction factor F will be some constant times Reynolds number to the power of minus n. Okay. When it is laminar flow, it is what, 64 by Reynolds number or 16 by Reynolds number, depending on whether you have a Darcy friction factor or Fanning friction factor. Okay. So, so in essence, when you have laminar flow, typically your B is equal to 16 and n is equal to 1. Okay. And this is for Reynolds number less than 2000. And then when you have turbulent, okay, a typical value, of course, this will change depending on your turbulent regime, but a good rule of thumb to use is 0.079 for B and n is equal to 1 by 4, okay, as a good starting value. So, you could have the liquid phase being laminar, gas phase being turbulent, or the other way around. Okay. So, your Martinelli parameter is sometimes determined, sometimes people call it as XTT, where both flows are turbulent, okay, or you can have XLL, well, both are laminar, or you can have XLT or XTL. Okay. And so, that subscript tells you which phase is turbulent, which phase is laminar. Does that make sense? Okay. Now, how we use the Martinelli parameter, I am going to come to that in a minute when we discuss the different correlations. Okay. And there are 100 different correlations, we do not have time to get into them. I will cherry pick a few and illustrate it for you. Okay. So, now let us look at horizontal flow, horizontal adiabatic two phase flow. So, in horizontal adiabatic two phase flow, things are not uniformly distributed. Okay. Even if you have bubbly flow, the bulk of the bubbles will tend to stick to the top. Okay. So, this is stratified bubbly flow instead of homogeneous bubbly flow. So, in a vertically oriented pipe with flow in the upward direction, you are more likely to have a homogeneous bubbly flow. Here you have stratified bubbly flow. So, that tells you, depending on the type of flow configuration you have and the flow regime you have, the type of correlation that you want to use will be different. And so, therefore, there are 100 different correlations out there, and each of them correlations are very limited in their scope. The first limitation is you have to know before you use it what was the flow configuration under which it was developed. Okay. And then it might have limits on the validity of the Reynolds number, and you are dealing with two different Reynolds numbers. Okay. Reynolds number for the liquid, Reynolds number for the gas, and you have to be aware of the limits of both of those Reynolds numbers under which those testing was done, and your results are only valid for those range of Reynolds number and for that diameter tube. Okay. Because you can see that depending on the diameter of the tube, what you would classify as slug flow in one case in a smaller diameter tube, okay, might be a churn flow for a bigger diameter tube for the same Reynolds numbers. Okay. So, just looking at two Reynolds numbers is not enough, you have to make sure you are looking at the same diameter tubes as well. Okay. So, it becomes very complicated, and so that is why two phase flow is ripe for artificial intelligence and machine learning, because the parameter space is so wide, it is very difficult to come up with a unified set of principles. And so, I think that is going to be a very rich resource research topic in the next 10 years, that is people are realizing right now. Okay. So, those of you who have a knack for artificial intelligence or machine learning and for two phase flow, that is a great topic to be in. okay, because there are so many disparate correlations out there, and each of them are valid for only such a small part of the whole flow map. And a priori, as a human mind trying to figure out, okay, my boundary ends here and my boundary ends here, it's very difficult to figure it out in your head. And the computer can be very good at doing those classifications, those if then else statements for 100 different correlations, right? And that's what neural networks do. Okay. So I digress, but that's actually a very interesting topic. I think it's an emerging topic. Maybe 10 years from now there will be, or 5 years from now there will be a Gyan course on that. Okay. So anyway, so there is bubbly flow, and then you can also have annular flow, or well, you can have plug flow. But even in the plug flow, your plugs will tend to stick towards the top. And you can immediately see there is a asymmetry in the flow, right? Isn't it? And then you get into annular flow, and even your annular flow will be skewed, because you will have more liquid in the annulus in the bottom and less liquid in the annulus on the top. In other words, if I look at the cross section, I will see more of the bubbles in the top. You know, if I look at this cross section, the plug will be more towards the top. If I look at the annular flow, this is how the annulus is going to look like. I will have more liquid in the bottom. Okay, and then of course you can have wispy annular flow and so on, but you can also have what is known as stratified flow, where there is no liquid in the top and the liquid is in the bottom. So if I look at it, that's my stratified flow, and depending on the relative difference between your UG and UL, that will determine the type of waves that are going to form on the surface, and whether they grow with time or they shrink with time or they damp out with time. Okay. Now you can also have the stratified flow can also be, depending on the magnitude of these waves, they can also be classified as wavy flow. When you have too high a wave, you know, you can have wavy flow, and if these waves become too high, they might touch the opposite side of your, okay, you can have a situation like this, that the sloshing went and touched the upper portion of your tube. Okay. So, and you know, it's going to be very periodic, very transient, and so this is what is known as slug flow. Now there are a few exceptions. I mean, in general, when you have big pipes, you know, this is the type of flow regimes you get, but when you have very small tubes, there are two other types of flows that come in. Okay. And when you have very large tubes, then you have another type of flow, what is known as capillary flow. Okay. So in capillary flow, what happens is you have tiny droplets, and because of the shear, they have a teardrop shape. Okay, and so this is known as capillary flow, and this tends to happen when you have very large diameter tubes or pipes, and your liquid flow is very small, and the bulk of it is gas flow. Okay. You also have another type of flow which happens in very small diameter tubes, particularly with respect to microchannels, and when the flow rate is very small. Okay. And that is known as a capillary bubble flow. Where you have this capillary liquid trapped in between gas bubbles. This typically happens when you are trying to have a carbonated beverage using a plastic straw. Okay, that is a classic example of having a capillary bubble flow, where sometimes the carbon dioxide from the flow itself comes out, forms small trapped gas bubbles in the straw, or it could be because the flow rates, the rate at which you are drinking the carbonated beverage, can have different gas flow regimes in it, and you can end up with this type of flow. Okay. Now, when it comes to power plants, there is one other type of flow that comes in, and that is known as mist flow, where you have pure vapor in the pipe, but you have dispersed droplets of superheated liquid like a mist, and these droplets, they impinge on the heater surface and they bounce off like billiard balls. The reason is, every time they are touching the hot surface, it is generating steam, and the steam causes like a rocket engine effect. It bounces off like a rocket nozzle essentially. Okay. And so that is what is known as a mist flow, and this happens right before the steam is entering your turbine. And one of the things that you have to assure is this mist is completely vaporized before it enters your turbine, because otherwise it will corrode your turbine blades. Okay. So, a big part of two-phase flow is to make sure that you are eliminating those mist, you are getting complete evaporation of your liquid, and that is the most enigmatic part, because it is very difficult getting rid of the mist. Okay. And when we talk about the heat transfer, we will see why that complication comes in. Okay. So, now that we have looked at the different flow regimes, so a good way, if you think about it, now this is I've been discussing things where there is not really that much of a heat transfer involved. Okay. But now consider a pipe in a boiler. Okay. So, I have a pipe that is in a boiler, I have hot gases flowing on the outside, and the liquid is coming in. Okay. So, at some point I will start nucleating vapor bubbles on the surface of this pipe, and these vapor bubbles are going to depart, and I am going to form a bubbly flow. And so, this is where I have onset of nucleate boiling, ONB, right. And then eventually the bubbles are going to coalesce, and they are going to form bigger bubbles. Okay. And these bigger bubbles are going to join, and they are going to form bubbles that are of the same size as your diameter of your tube, and that happens to be your slug flow. And you do not have pure slug flow, you have a little bit of bubbles also, small bubbles also with your slug flow, and then two of these slugs will join up together and form a big churn, and so that is your churn flow, and then eventually you will form an annular flow. Okay. So, you get into your annular flow, and then because of Helmholtz instability, you have entrained some of the droplets out, and so you are going to get misty flow, and finally, if your design is done right, all this mist will evaporate, and then you will have pure vapor flow. So, we will not have too much time to talk about flow instability in two-phase flow, but I will just do a very brief discussion. Okay, without, sorry, should we take a time out? Yeah, I think, yeah, let me finish with this part before, and let us finish the philosophical discussion, and then we will come back for the break. Okay, 5 more minutes. Now, I will not get too much time to talk about the flow instabilities in flow boiling, but let us just have a quick philosophical discussion. Okay. So, let us say I am plotting the pressure drop in a pipe as a function of flow rate. I can do the pressure drop in a pipe as a function of velocity, right? And I will get a straight line. Now, I can do one for vapor, one for liquid. So, let us say I have a tube, I am coming in with uniform mass flow rate of liquid, and I am going out with uniform mass flow rate of vapor, same mass flow rate, right. So, if I plot if I have the properties of vapor, I have the diameter of the tube, I know what the mass flow rate of the liquid is, and so therefore, that should be the mass flow rate of the vapor that is exceeding the system, exceeding the system. Everything is at 100 degrees Celsius. So, my pure liquid is at 100, my pure vapor is at 100. Okay. So, I plot the pressure drop as a function of the mass average velocity. Which one of this is liquid, which one of this is vapor? Okay, so, the top one will be liquid, the bottom one will be vapor. Yeah. Let us assume I have chosen my parameters such that both are laminar. It is more likely your liquid will come in laminar, your gas will leave, the vapor will leave turbulent, because you have a higher volume, almost 1000 times more volume going from liquid to vapor, right. But let us say both are, I choose my parameters in such a way that my incoming liquid is laminar, my outgoing vapor is also laminar. Okay. So, that way we are doing an apples to apples comparison. Now, I do the same. So, if I were to translate this data and I do the same plot, but now I do it with respect to the mass flow rate, which one is liquid, which one is vapor. What do you think? Or in other words, for the same flow velocity, I will get lower pressure drop for the vapor and higher pressure drop for the liquid, isn't it? So, if I have the same mass flow rate, which one is liquid, which one is vapor? Come again? The bottom one is liquid. Why do you say that? Come again? Okay. So, you use the equation. Okay. So, what equation did you use? Okay. But then why should the higher density fluid, which is liquid, give you a lower pressure drop? So, what you are saying is the higher density liquid will give me a lower pressure drop, isn't it? Or the higher viscosity fluid will give me a lower pressure drop, isn't it? You are right. But what is the justification? You cannot just pull an answer from the sky. There has to be a mathematical justification, right? Okay. In the interest of time, let us move on, but you are right. This one will be the liquid, this one will be the vapor. So, now think about it. When I am coming into the pipe, I am riding up this graph, isn't it? But at some point I need to transition from here and climb this graph, isn't it? Does that make sense? So, in other words, that transition will happen if my graph looks like this. In between, my graph is doing this, right? Let me draw it out on a bigger piece of paper. So, this is my vapor plot, this is my liquid plot, and at some point I am going this way, and then at some point I have to go on this graph. And so, and things are not jumping abruptly, right. So, things are going smoothly. So, at some point I will have to drive on this graph before I start climbing this graph. Does that make sense? For things to be continuous, the slope has to match here, the slope has to match here for this intervening curve that comes in. Now, if that has to happen, I get a part of the curve where my mass flow rate increases, but my pressure drop decreases, and that will make my system unstable. It is kind of like transition boiling, where you increase your delta T and your heat flux decreases, okay, and that makes your system unstable and very transient. Okay, so, that is one instability. We are going to look at the equations, but let us just look at it from the, let us take an overview of what kind of complications you are dealing with, right. Then the other complication you are dealing with is typically in a boiler, you will have an inlet plenum, you will have an outlet plenum, in between you will have these pipes, an array of pipes, and they are being heated by the hot flue gases, for example. If you have a gas fired burner or a coal fired burner, you have these hot gases at 300 to 500 degrees Celsius moving on top of these pipes, and the liquid is coming in, and on the other side I am getting out as pure vapor, because I cannot afford to have any liquid droplets in my flow, it will kill my turbine. Okay. Now, if I have a parallel set of these pipes, it creates its own problem, which is, let us say all of them are pumping pure liquid, and then one of them forms a small vapor bubble in the pipe. What has that done to the average density of this, or average viscosity of this flow? If I were to treat it as a homogeneous fluid, now I got to replace it with a fluid which has a lower viscosity, average viscosity, and because it has a lower average viscosity, what happens? The pressure drop in that pipe is smaller. So, I am coming in with a uniform pressure P1 over here, but if I look at the local pressure here, P2, let us say PA prime, PB prime, PC prime. Now, that this one has a lower pressure drop, my PB prime will be higher than PA or PC. Okay, what will that cause? It will cause a part of the flow to start pushing back on these flows, because that is at a higher pressure. Does that make sense? And so, pretty soon you might end up with its own circulating loop over here, where the flow is actually trying to go backwards, while the other pipes are pushing flow forwards. So, you could have localized areas of flow reversal, okay, and that is what is known as leading edge instability. Okay. So, there are lots of different types of complications that come in when you have two phase flow compared to when you have single phase flow, especially when it involves some kind of evaporation or condensation. Okay. Let us take a quick break, and then we are going to look at the math and the numbers. So, there are a couple of videos I wanted to show you yesterday. Okay. So, I am glad that I am able to show it to you today at least. And the first one actually refers to things I was discussing yesterday. So, let us look at this video to begin with. Okay. So, what do you think is going on? He is taking liquid metal, molten metal, which is probably what 500, 600 degrees Celsius. He is putting it in his mouth. You would think he would die, right? So, how is he able to survive it? Any idea? How is that possible? Come on, this is a two-phase flow class, you should know by now.
Temperature is almost constant when the freezing is taking place inside the mouth.
But it is still 500 degrees Celsius. Okay, let me show you one more video. Actually, I forgot to upload it, but hopefully I should find it right away. I don't know why the internet is so slow, but
You look like you're thinking of something pretty good.
I am. There's a myth going around that you can stick your hand into molten lead and not get hurt.
Molten metal. It's pretty nasty stuff. Just look at these shots of a foundry. It would seem that if you touched any of that stuff with your hands, you'd be horribly, horribly burned. But maybe not so. See, there's a myth going around that if you take pure lead and you melt it, that you can dip your hand in it and not be burnt or horribly injured. I know. The trick is supposed to be that you wet your hand before doing it, and it exploits what's known as the Leidenfrost effect.
The Leidenfrost effect? Well, seeing as it's the scientific basis for the myth, Adam, with his hot steel ball and fish tank, is on demonstration duty.
Wow! Look at that!
You can see a clear skin of, I guess it's steam around the whole thing. What you're seeing in this demonstration is known as the Leidenfrost effect.
It's like an atmosphere.
It's interesting because the steam that's created when you expose a hot surface to water is actually insulating that surface. And it makes sense because steam, being a gas, conducts heat less rapidly than the water itself does.
And that's the key. When cool water is exposed to an extremely hot surface, a layer of water vapor, which is a relatively poor heat conductor, provides a thin protective barrier. So it's time to get cooking for this hair-raising stunt.
Is this me?
With the one and only ingredient, lead.
Is this the first Terminator you've ever cooked?
No, I've done this a lot before, actually. Every time I get a robot that's misbehaving,
The problem is you gotta keep them cooking, otherwise they reformulate and try and kill you.
It's about 725 degrees.
well, that's about 100 degrees more than melting temperature. I think that's about right.
Let's do it.
Cue the stand-in digits.
This meat is raw, and if it actually gets too hot, it's going to change color because it's cooking.
If these finger-sized sausages sizzle, then Adam and Jamie won't be going anywhere near the hot pot.
Oh, no, that seems to be a problem, doesn't it?
A very slight change of color.
But also, lead stuck to... I wouldn't want that to happen to my finger.
No.
While not burnt by the standards of any backyard barbecue, the sausage is being cooked. But they're not giving up yet.
A hair's breadth over 800.
In order to avoid burning their stand-in digits, they're going to raise the temperature and try again.
Here's where we stand so far. Behind me is a bucket of molten lead, into which we have already stuck a couple of breakfast sausages and watched them get lead stuck to them and watched them get burnt. We're not ready to put our hands in there yet, but we hear that if we get the lead 200 degrees over its melting point. Great. That's 850. Let's try it. It'll stop sticking. Here's that finger, bucket of water. Whoop. Shake it off into the lead. And it looks pretty much perfect, and it's still cold.
Yeah.
So 850 degrees Fahrenheit is the magic number. The sausage comes through unscathed, which leaves just one question.
I'm game. You game?
I picture people yelling at their TV, "Go on, do it! You, go on, try it! Ah!" Aren't you? Yeah. All right. We're about to go for it. We're about to dip our hands into molten metal, and we've got plenty of evidence saying that this is safe. It's clear from our experimentation that the conditions to do it safely are actually pretty precise. I think we've got them. And I think it's going to be okay.
And this little piggy burned clean off.
Despite the sausage-based evidence, clearly a sentence never before used, there is still a healthy amount of trepidation. Remember, the lead is at around 450 degrees Celsius, which puts this stunt firmly in the "don't try at home" category.
Nothing. Now, I just went about that deep.
Yeah. You want to go a little deeper?
My little finger is just fine. Of course, I only went in about that deep. I was being a little careful. I didn't feel a thing. It felt kind of warm and pleasant, actually.
Go for it.
And a repeat performance with an index finger yields the same result.
Now, that one, it went in pretty good, and no problem.
No problem?
No problem.
I guess it's my turn.
Adam has had the luxury of using Jamie as a human guinea pig, so naturally, he has to up the ante. He's going for 4 fingers.
Here we go, ladies and gentlemen. One human hand in molten metal. Ho, 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 ho. That's freaky. You can feel the water boiling against your fingers. You can feel that right there.
And that pretty much puts this lead mini-myth to bed.
So Jamie and I just successfully dipped our hands into a pot of molten metal. No lie. The Leiden-Frost effect is no myth. It protected us. Well, I'm unharmed. You?
I'm fine.
That's all we needed. That's a myth confirmed.
Yep.
Okay, so now can you explain where did it go? How would you explain it then? Leiden-Frost, right? We studied it yesterday. So now think of convergence, right? So there could be societal applications of this that we have not actually explored yet. Okay, so but there are implications of what we are studying in theory to what can happen in real life. Okay, let me show you 2 more videos. Actually, I wanted to show these to you yesterday, but better late than never. Now, I know in several temples in India and then also in Southeast Asia, they walk on fire, right? Have you ever tried it? So, let us try these fire walking videos, okay? Yeah, the internet is a little slow in responding. So. All right, so let's go back to these guys, okay? So, you saw the finger sticking in the molten lead was a successful experiment, right?
It seems it's physics that keep your feet from being flame grilled and not mind over matter. Or is it? What about a mind unprepared? A mind unsullied by the certainty of science?
So, here is an example of an experiment gone
To
wrong.
find out, let's segue
Gone
to the
very
next
badly
stage.
wrong.
What are you cooking?
Okay?
We're going to be cooking, well, at the bottom of your feet.
We're looking at the science of firewalking.
Firewalking! Awesome!
Apparently, Adam would walk over hot coals to walk over hot coals. So Adam's ready for his trial by fire.
You can do it!
And remember, before Carrie, Grant, and Tori took their first hot step, they knew they wouldn't get burned.
You got to tell your feet.
My
to
heart
move,
rate
though.
just went up a bit. Okay.
But Adam knows nothing about the data and the technique of stepping lightly. Will he get across unscathed, or will those red-hot coals fry his feet? Ah, yes. Apparently so.
Wow! That hurt a lot. Al was going through my head. As I did it, walk, 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 this isn't so bad. Holy crap, this is pretty bad. Ah! Like that. That's about the thought process.
So it seems that it does matter what's in your mind, but only insofar as knowledge about technique and preparation go.
Your feet
My
to
heart
move,
rate
though.
just went up a bit. Okay.
But Adam knows nothing about the data and the technique of stepping lightly. Will he get across unscathed, or will those red-hot coals fry his feet? Ah, yes. Apparently so.
Wow! That hurt a lot. Al was going through my head. As I did it, walk, 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 this isn't so bad. Holy crap, this is pretty bad. Ah! Like that. That's about the thought process.
So it seems that it does matter what's in your mind, but only insofar as knowledge about technique and preparation go.
With no prep at all, I think I made a classic mistake of speeding up and digging my feet into the coals more.
Yep, Adam's hard marching method meant some of the coals stuck to his feet, giving them more time to conduct their heat. Ouch.
Hey, it's me.
And after a call home with the not-so-good news,
So I just walked on hot coals, and I burned the hell out of my feet.
let's break out the burn cream and get this myth wrapped up.
Okay, so Leidenfrost didn't work. Okay, but if you go back and look at the videos in the temple,
Seems it's physics
in
that keep
India,
your feet from being flame grilled and not mind over matter.
so let's look at the same video, but people doing it in India. Okay, you get the point. We don't need to see the whole video. So how is it that Leidenfrost point is working in India and not in US? What would your guess be? Come again? No, that guy was also running. Yeah. You know, so the way it's done in the temples is they actually go for a dip in the water tank first. And so, when you are dipping your feet in the water, you have a film of liquid trapped in your feet, versus this guy just took his leg out of his foot out of his shoe. It was probably dry, so there was no water to create the steam, and he burnt his feet. Okay, so that at the end he mentioned that the technique matters. Okay, and he was rationalizing it. Oh, I got more conduction and all those things. These guys don't know boiling, so that's why they were explaining it in the wrong way. Okay, so anyway, so that's as far as film boiling that I wanted to show you yesterday. And then the other one that I wanted to show you for today, since we are dealing with two-phase flow, it's not a pool boiling situation anymore. We have some kind of flow going on, right? Now, you all have heard about this geological phenomena called geysering. You have a geyser in your bathroom, right? So, how does geysering work? Any idea? What's a geyser to begin with? Can anybody tell me? Okay, so what happens? So, all of a sudden there is a what's the Hindi term for a water spout? Fawara, right? So, all of a sudden that comes out of the ground. Why does it come out? This water shoots out of the holes in the ground, right? So, let me show you. This is actually a very famous national park in US, in Wyoming. It's called Yellowstone National Park, and every day thousands of people come to see this one particular item in that park, which is known as the Old Faithful Geyser. And this geyser, I have gone and visited it, almost to the dot every hour comes out with a spout of water, and it goes up pretty high, something like 100, 200 feet, almost like 100 meters high. It shoots up water for 100 meters or so for 5 minutes, and then it stops, and then again after about an hour it shoots up. And it's not possible to predict when the next one will happen. I mean, it's possible to predict, you cannot predict long term. Okay, so within like a couple of minutes accuracy, if you know the history of the previous 3 outputs, you can predict the next output, but that's about it. Okay, because there is about a 1 to 2 minute variation or 5 minute variation between each of these outputs. That gets into boiling chaos. Okay, I'll see on Friday, if I have some time I will get into it. So, what chaos theory says, if you look at a pendulum, it will always swing with the same amplitude and periodicity, right? But if I connect 2 pendulums together, they will start feeding into each other, and the amount of swing that you get from each cycle to cycle will actually start varying, and that gets into the realm of chaos theory, where it will be almost what you theoretically predicted, but there will be a standard deviation on that prediction. Okay, it will never hit that right number twice. Okay, it will move around that number, but at each swing it will be a little different. So, it's the same thing with boiling chaos, and with this geysering is a very good example of that, is that your bubble, every time it departs, you are predicting it's going to depart once every 100 millisecond, but if you fix your attention to one nucleation spot, you will see that it will never be exactly 100 millisecond. Okay, it will oscillate around that 100 millisecond, but going from one cycle to the next, each time it will be a slightly different. Okay, that's a chaotic process where it's not exactly periodic, but very close to being periodic. Okay, so anyway, so let's look at this video.
Mamas? Wow! Mamas, yeah. Wow. Whoa. Right, close your eyes. You don't want to see that, right?
Woo, higher. Is it over?
So it goes up higher?
Wow. Okay, it's getting shorter. That's really cool.
Okay. So, how is that happening? That is a classic example of two-phase flow and two-phase flow instability. Okay. So, whoops. So, how does geysering happen? So, typically, geysering happens in volcanically active, geographical locations. And so, typically when you have, recently you all saw the volcanic eruptions in Hawaii, for example, right. So, and actually I have been to that volcano when it was dormant. And one thing that strikes you, whether you visit Yellowstone National Park or these volcanic areas in Hawaii, is the strong smell of sulfur that comes out. It's a lot of sulfuric acid in the air, in very tiny concentrations essentially. But essentially, geyser happens in a volcanically active location or geothermally active locations. And so, what happens is you typically have these fissures in the rock. You kind of have all these cracks in the rock, and typically you have sort of a water supply from a nearby lake that constantly is feeding water into these formations. So, this is typically full of water to begin with. Okay, so this is all full of water. But then, because it is a hot rock, and there is lava somewhere down here that's constantly feeding heat into this body of water. But this one is going pretty deep, so you have a big variation in pressure, because you have a rho GH, right, of pressure at the bottom over here. So, the pressure here is actually much higher than the pressure here, which means, so if I look at P1 here and P2 here, your P1 is much greater than P2. So, therefore, the T sat here is much greater than the saturation temperature here. And so, let us say one geysering event has happened, the water went out, fresh cold water seeped in from the lake nearby, water body nearby, and that water starts heating up. But the one at the bottom is probably going to heat up at a faster rate, because it is getting more heat than the one on the top. But then this one is actually at a higher boiling point, and plus on top of that you need that excess temperature of 5 or 6 degrees Celsius before nucleation will occur. Okay? But the moment you nucleate vapor bubbles in this bottom portion over here, the average density here has changed, and the moment nucleation happens here, average density changes, average pressure changes, and all of a sudden the Tsat drops. So now your boiling point, instead of being 110 degrees, has become 105, and the rock around it is probably at 115 or 120 at that point, and now you are very close to critical heat flux all of a sudden. And so then all of a sudden a massive amount of water spontaneously becomes vapor. Okay, and once that vapor bubble forms, it creates a shock pulse, and all that vapor wants to leave, and in that process it drags the whole mass of liquid and lifts it up as that steam is leaving the system, and that's when you get the whole water spout coming out. And once the steam leaves the system, the water is dragged out with it, the whole process repeats. Okay, so that's how a geysering instability occurs. Okay, so these are things I wanted to show you in the morning before I went into the math, but now let's get into the math of it. Okay, so any questions so far? No? Yeah, go ahead. Yeah, you can do it with aluminum also. What's that? What else would you like to use? No, oils will not go above 500. Typical oils, they crash and burn out at around 400. Most oils actually burn out at 200. Right? There are only a few heat transfer fluids, oil based heat transfer fluids, that exceed 200. Most of them have the operating temperature in the range of about 80 to 150. So if you exceed that, then your options are liquid metals that are used in nuclear reactors, molten salts, all right, or eutectics like lead based eutectics. Okay, so that's why they did it with lead, because lead of all the metals in that temperature range has the lowest melting point. Of course, mercury has the lowest melting point as a molten metal, but after mercury you are probably looking at lead. Okay, does that answer your question? Yeah, it's more a materials thing rather than a heat transfer thing, but let's see. So we looked at the different flow regimes. Now the next thing is when you have heat transfer occurring, how would your flow boiling maps change, right? So here is one example of Teitel and Ducler. They were faculty members in University of Houston. Okay, and they were the first to come up with sort of a flow boiling map for flow in a pipe with some kind of phase change happening. Okay, and so this is how a typical graph looks like. All right, so remember the previous one that I showed you was based on the liquid and vapor momentum. Okay, but in the Teitel and Ducler map, they based it on Martinelli parameter, which is sort of related to momentum. Momentum and pressure drop are related, and that goes on the x axis. But he came up with these other parameters that he called FTD, TTD and KTD. Okay, and so those are the ones that are plotted on the y axis. So on the secondary y axis you have plotted KTD, on the primary y axis he has plotted FTD and TTD, and the definition for FTD and TTD are given over here. Okay, and so these are still similar to the momentum and pressure drop parameters, but they are modified momentum and modified pressure drop parameters. And based on these modified momentum pressure drop parameters, they were able to generate a map where they could go from let's see, they could go from dispersed bubble flow to intermittent churn flow to stratified flow to stratified wavy flow, annular flow, and which regime your pipe is in is determined by what the value of FTD, KTD and TTD is. Okay. So if it involves some kind of phase change, then you have to calculate all these three parameters, and then based on the value of all those three parameters you figure out where you are on the graph, and that's how you predict whether you have bubbly flow or annular flow and or so on for a given segment of the pipe. So, in other words, you separate your pipe into different segments. For each segment you calculate these 3 parameters, and based on where that point lies you sort of predict, okay, for this part of the pipe it is bubbly flow, this part of the pipe it is annular flow. Does that make sense? Okay. Now, what is the governing equations for each of these? That is there in the note. In the interest of time I am not getting into those details, but you know the equations that define each of these curves are there in your notes. Okay. So, that is how a flow boiling map is constructed, or a flow boiling map is used to figure out the flow regimes. Does that make sense? Okay. And I apologize, I am skipping it because there are a lot more other stuff to cover, and that is more basics of 2-phase flow, because this is more advanced topic. So, I want to spend more time on the advanced topics part of the 2-phase flow. Okay. So, that is as far as you know the flow boiling maps are concerned, and as you can see this Martinelli parameter becomes a very important factor here. Okay. So, yes. So, again you know if you have different diameter pipes or tubes, you got to come up with your own you know flow boiling maps. So, you can use this particular flow boiling map if I forget what diameter pipe they use, but if you go look up the references they will tell you what diameter pipe was used and what Reynolds numbers and flow rates were used. So, as long as you are within those zone of those flow rates and Reynolds numbers, you are fine to use these equations. But if you go outside of the range of these equations, then it becomes very uncertain that the predictions that you are making are correct or not. And so, in that case the only recourse is to go and regenerate your own flow boiling maps and then use that. Okay. So, any other questions or? No? All right. So, the next thing we want to look at is how do I model this 2-phase flow, right. Now, so let us take a very simplified approach, and you know if you look at the NPTEL courses, there are a few NPTEL courses that get into the details of these models. This is going to be a sort of a repeat of what is already out there, but I am going to do a very quick one, a quick review, okay, before we get into the more advanced topics, so that everybody is on the same plane. So, let us consider a situation where okay, so let us say you have an inclined pipe, and the inclination angle of the pipe is let us say omega. Okay, and let us, for simplicity's sake, let us just assume that you have a sort of a stratified flow, where a part of the flow is in the liquid phase and part of the flow is in vapor phase. Okay. So, let us say the orientation of gravity is in this direction, okay, and I am going to take a small control volume in this flow, and if I plot it, I will have a pressure here on this side and a pressure here P plus dP on the other side, okay, and you know, and I am doing a one dimensional model, which means if this was a pure one single phase pipe flow, I would get a parabolic flow profile in the pipe, isn't it? But if I were to approximate it as a one dimensional model, then I would have a plug flow, everything being of uniform velocity. I am neglecting the velocity variation in the cross section. Okay, whatever velocity I assume it to be constant in the whole cross section. Okay. And so, in this situation my vapor will flow with one velocity. Okay, so, the area occupied by the gas is let us say Ag, the area occupied by the liquid is Af, okay, and the mass flow rate of the gas going in is m dot g, and the velocity of the gas going is ug. Similarly, the velocity of the the liquid going in is m dot f, the velocity of the liquid going in is u f, okay, and correspondingly the mass that is coming out on this side is m dot f plus d m dot f, and the velocity that is going in is u f plus d u f. Similarly, in this direction it is m dot g plus d m dot g, and then it is u g plus d u g is what is exiting the system. So, you can see it is very similar to what you have seen in your undergraduate fluid mechanics, is not it? You know, we do a similar kind of analysis. Now, now I am assuming that the area is not constant. So, at the inlet point, if the area is A f and A g, on the outlet side my area can also be different, it can be A f plus d A f, and on the outlet side this could be A g plus d A g. In other words, it can be a converging diverging pipe, or diverging, it could be a converging pipe, it could be a diverging pipe. Okay. So, let us see what else am I missing. Can you tell me what else is missing in this diagram here? So, I have plotted the pressure, right, which is what, a surface force or a body force? Okay. So, are there any other surface forces in the system? Okay. So, where will be the shear force here? On the wall, right. So, let us say because the flow is in this direction, so I expect a shear force in the liquid phase to be in the opposite direction on the wall. So, this is the shear force at the wall from the fluid side, liquid side, and then I will have a shear force on the wall from the gas side. Anything else? There is a shear at the interface. Okay. And so, if I assume that the gas velocity typically is higher than the liquid velocity, okay, so then I would assume that there is a force at the interface, let us call it as df I g on the gas side, okay, and then I would have a shear force that has to oppose this shear force, is not it, from the liquid side. So, that would be df I f, and typically your df I g should be equal to negative of df I f, is not it, under equilibrium conditions. All right. So, if I were to write down the equations for this configuration, well, first of all I will have a u g and a u f. Okay. So, from my mass balance I will get u g, that is g x divided by rho g alpha, alpha is the void fraction, is not it, and similarly I will get a velocity of the liquid phase which will be the mass flux divided by the density divided by the fraction of the area in which my liquid is flowing. Do you all agree with me? Does this equation make sense? Okay. And then the other equations that I need to care about are my total mass flow rate at any cross section is going to be same, and that is going to be equal to the gas mass flow rate and the liquid mass flow rate, or I can write down this same equation in terms of my mass velocities as rho g times g x times a plus rho f times g times 1 minus x times a. Okay. And so, mass flow rate is constant. So, dm dot is equal to 0, which means that dm dot g should be equal to minus dm dot f, which means if I have 1 gram of liquid becoming vapor, okay, so that means my liquid mass flow rate will change by go down by 1 gram and my vapor mass flow rate will go up by 1 gram, okay, per second, let us say. And so, similarly, if I take this equation and if I take the derivative of this equation and set it equal to 0, so my dm dot dz should be equal to 0, which means my d dz of rho g gx a plus d dz of rho f g times 1 minus x times a should be equal to 0. That is fairly straightforward, isn't it? Now, the place where things get, so this is my mass conservation is what we are dealing with right now. Life becomes complicated when you have to deal with momentum. Okay, so let us look at momentum conservation. Okay, so let us do a force balance. So, what will be my force balance? Well, I got to balance my surface forces first. So, P times this area is what is coming in, and then P times area is what is opposing it. Okay, so, this is my positive z direction, is not it? Okay, so, P times Ag, I am just doing the balance on the gas side first. Okay. So, my control volume to begin with, first I look at the gas side control volume, which is this is my gas side control volume, is not it? So, I am looking at that control volume first. So, I have P times Ag minus P plus dP times Ag plus dAg. Okay, and then what else? I have a dFg that is in the negative dz direction, and then I have a negative dFig at the interface. Okay, anything else? Body force, right? So, what is the volume of this control volume? So, it should be Ag times dz approximately, right? That is the volume times rho of g, that is the mass, times gravity, but that is pointed in the downward directions, and I need it in the component of that gravity along the flow direction. So, that should be equal to, is it cos or sine? It is sine omega with a negative sign, because if gravity is pointed downwards, the component is in opposite to the z direction, is not it? Okay. So, that is sum total of my surface and body forces, okay, and that should be equal to change in momentum, is not it, across the control volume. And since we have assumed a 1D velocity profile, so basically what is the momentum going out? Well, it is m dot g plus dm dot g times ug plus dug is what is going out, okay, and what is coming in is m dot g ug. Anything else? Is there any other momentum coming into the system? Okay, so the amount that is vaporizing and becoming vapor is dm dot g, isn't it? That is coming from the liquid phase. And that what velocity will that have? It will have a velocity of uf, minus uf actually. Does that make sense? Okay, actually it is plus uf, but I am subtracting the momentum coming into the system essentially. Okay. So, similarly I can write one for the liquid phase as well. So, if I write it for the liquid phase, I will follow the same things. It will be PAF minus P plus dP times AF plus DAF, and then minus DF. Okay. What about the DFIF? Is it positive or negative, the interface? Because in the vapor I assumed it was in the negative direction. So, for the liquid it has to be equal and opposite, in the opposite direction, and so it becomes positive. So, I am going to add DF plus D of FIF will get added, okay. And then of course minus AF times dz, that is the area, times density gives the mass, that is the volume times density gives the mass, that times g gives you the body force, and then sin omega. Okay, and that should be equal to again the momentum flux in the system. So, you have m dot f plus d m dot f, and then uf plus d uf, okay, and then you have d m dot f uf, and then minus m dot f uf. Okay, so, this is the momentum coming from that it is losing, because a part of it is going into the vapor phase. Okay. So, all right. Now, for steady flows we know that this df if is equal to minus df ig, okay, under steady state conditions. So, if I add both of these two equations, what will I end up with? Okay, if I add these two equations, I will end up with minus A dP, okay, where A is the total area, minus PdA, okay, minus dF of f, minus dF of g, and then minus AF rho f plus AG rho g times g times dz times sin omega, and that should be equal to d of m dot g ug plus m dot f uf. Okay. Now, what I am going to do is I am going to club these two forces that come from friction, dff and dfg, and I am going to account for one friction factor. Okay. So, I am going to say that df of f and plus df of g, this comes from friction, and so that is equal to minus dp dz friction times A times dz. I do not know what that is, I am going to calculate that a little down the road. Okay, and then the other approximation, or juggling of mathematical quantities I am going to do is I am going to introduce void fraction. So, void fraction is Ag by the total area. Okay, so, if I do all these, then I will end up with a equation that looks like this. So, I have a minus dP dz. Okay, so, that will be equal to minus P by A times dz by dA. Okay, and then I am going to have a minus dP dz because of friction. Okay, and then I am going to end up with 1 minus alpha times rho f plus alpha times rho g times g times sin times omega. So, 1 by A times d dz, your g x a whole square divided by rho g alpha plus g times 1 minus x times a whole square divided by rho f times 1 minus alpha, and that should be equal to 0. I am sorry, not 0. So, okay, so if I look at each of these components, well, this guy comes in, this is variation in pressure due to change in cross section, isn't it? Because as the area changes with z, if you have a constant cross section pipe, this dz dA or dA dz will go to 0. Okay, this whole thing comes in because the pipe cross section is changing. So, if you have a pipe of constant cross section, I do not have to deal with this guy. Okay, the other complication that I am dealing with is this pressure drop that is coming because of viscosity or friction. Okay. And then if I look at this third term over here, this is nothing but the body force, the gravity head. If omega is 0, which is a horizontal pipe, then it goes to 0. Okay. So, at the simplest level, if I take a horizontal pipe of constant cross sectional area, these two terms disappear. That is the simplest case I can think of, right. But I still have to figure out this dP dz friction, and I still have to figure out how this alpha, the void fraction, changes from one location to another. That is the whole enigma of two-phase flow. You know, if you had a reliable way of predicting alpha, and if you had a reliable way of predicting this dP dz friction, a lot of our complications in our life will go away. But unfortunately, life is not that simple. Okay. And that is where the flow regimes and the flow oscillations come and complicate your life. It is because of these two terms. Okay. These two terms are highly time dependent, space dependent, and then if you have instability in your system, you know, on any 2 days, you know, depending on the phase of the moon and whether your dog, you know, had a bad health that day or something, right, these things will change. In other words, there are a lot of factors that can go and affect it, which are beyond your control. All right. So, now the other thing to look at is this term over here, this 1 by a d dz component. Okay. So, this is the acceleration of your flow. Okay. So, this is the pressure drop that is happening because there is a acceleration or inertia in your flow. Okay. So, now we are going to simplify this equation, because this is an introductory class. We are going to look at the most simple situation, but before I go there, let me ask you a very fundamental question. Okay. So, the fundamental question is, let us say I have a steady flow and I have a converging pipe. Okay, let us say the cross sectional area here is 5 meters square. Let us say the cross sectional area here is 1 meter square, and I am coming in with 2 meter per second. What will be the exit velocity here? What do you think? 10 meter per second? It is an incompressible flow. What is the acceleration? It is a steady flow. So, if I am sitting here, the flow is always 2 meter per second. If I am sitting here, the flow is always 10 meter per second. So, is the flow accelerating? It is, but if I am sitting here, the flow is not changing, because your definition of acceleration is dv dt, right. So, by this definition there is no acceleration. Okay, so then tell me what is the value of acceleration. Let us say this is about 100 meters long. Mm-hmm. Okay, so then what is the value of acceleration? Mm-hmm. So tell me, what is the equation you are going to use? Okay, so what is that? Okay, so I am going to use del V del T plus, come again, V, okay, times grad V, right. So since this is a one dimensional situation, or I can write d dx because there is only one parameter here. I can, instead of writing del, and it's not changing with respect to time, so this is 0. So how much is this? Yeah. So is the acceleration at this location and the acceleration at this location, are they the same? Come again? No, I am fine, but tell me a number. So what is A1 and what is A2? Hundred meters, yes. So you are saying it's 0.08 meters square per second at A1, and how much is it at A2? Do you all agree? Anybody has a different viewpoint? How are we doing on the time, by the way? Oh, it's almost 1. I guess we got to stop here. Okay, let's reconvene after lunch. You guys tell me if this is correct. What one of your colleagues here gave you a number, if that number is correct or wrong. Okay, so let's start at 2:30, right? Or should we start at 3? 3? Okay, let's start at 3. So make sure you tell your driver, the new time. Okay, all right. So.